Hello, and welcome to today's E360 webinar titled Navigating the CO2 Refrigeration Landscape, brought to you by Emerson. My name is Kate Henderson, and I will be your moderator for today. We have just a few announcements before we begin. Please note that this presentation's audio is provided by phone or through your computer's sound system. In addition, you may type questions that you have into the text area and hit send in the Q&A panel throughout the webinar. We will answer questions at the end and send out answers to questions that we may not get to in the coming days. If you'd like to revisit key sections of today's webinar, it will be available on demand at e360hub.emerson.com/webinars a few days after this live event. You'll also receive an email in the next few days with a link to the recorded event. Discussing today's topics will be Andre Patenaude, Director, Solution Strategy, and Brent Cheshire, Manager, End User Services. Andre is responsible for supporting system-related innovation and leveraging Emerson's global cold chain to drive adoption of integrated solutions in North America. He most recently led marketing efforts pertaining to Emerson's food retail and chiller markets. Prior to that, he had managed Emerson's global CO2 development. Andre has more than 35 years of industry experience in sales, marketing, training, and business development of HVACR system architectures and applications with compression and component technologies. He is a certified mechanical engineering technologist, MET, since 1984 and is a member of AHRI, ASHRAE, and RSES. In his role as Emerson's manager of end user services for the cold chain, Brent takes a holistic approach to helping customers solve problems. His responsibilities include, but are not limited to, technical SME engagement, coordination among our technical support, ProAct, customer success, solution sales, and product management teams. In addition, Brent has responsibilities in driving various Emerson CO2 programs and initiatives. Among 11 years of Emerson service, Brent has more than 10 years of CO2 experience, including over 250 transcritical CO2 system startups across multiple end users and OEMs. Previously, he worked for 8 years on our field services and application engineering teams with varying responsibilities that included startup and commissioning services, troubleshooting, product selection and site implementation, and customer training. In addition, he has 9 years of refrigeration technician experience. Brent earned a bachelor's degree in refrigeration and HVAC technologies from Sydney Institute of TAFE. The webinar will now begin. I'll hand it off to Andre and Brent.
Great, thank you very much, Kate. Really appreciate the introduction. I'm really thrilled to be here today to talk with actually Brent. You just saw that Brent's got over 250 transcritical CO2 startups under his belt, which is absolutely phenomenal. So it's great to have someone with that type of knowledge present with me today. So I'm thrilled to have Brent on board with that. As we get into the topics today, before we get into the main agenda, I'm going to have a grounding regulatory slide. So I'll go through that, talk about that, and at the end of that slide, I'll talk a little bit about why CO2 is so important to our industry. And then from there, we're going to get into what you need to know about CO2 differentiating factors versus HFC. And if you're a young technician or you're an experienced technician but never worked on CO2 before, or you're a new engineer that's going to be designing work systems, there's some certain things that you need to kind of know from a basics perspective about CO2 versus HFC. So we'll try to cover those. And what I'm going to try to do with the seminar, because Brent's on board here, of course, is that I'll be talking about leading up the slide and then passing it off to Brent and asking him from a service technician's perspective and his experience in the machine room, what his comments are on it. So we're going to try to kind of work that into the conversation as we move on with the seminar. I'll take a few minutes to talk about Emerson's high ambient, not Emerson's high ambient strategies, but high ambient strategies in general. What Emerson has done to invest and kind of understand the impact of these different high ambient strategies to improve efficiencies, and how we use that information to provide higher valued conversations with our customers. So I'll talk a bit about that. And then the meat of the presentation, if you will, is going to find in the system baselining. And it's all about, it's not meant to be a guide 100% step by step. It's a directional on system baselining, a CO2 system, and also some startup. So we'll go through that, and again, leverage Brent's experience in all these startups when we go through it. One thing as well is that at the end, we're going to get a case study, which is really a CO2 transcritical booster application that we collaborated with an OEM, and I'll talk a little bit about that. And we'll finish off of where you can find various information about Emerson, CO2, and other strategies. So from a regulatory perspective, you've probably seen this slide on August 4th when Kurt Kanapke and Katrina Kreitz presented. This is a great slide because it's a summary of most of the activities that are going on. And if we start, of course, on the left of the chart, California has been kind of leading the state's pack, if you will, from a regulatory perspective to phase down HFCs. They, back in, I believe it was 2019, they implemented SNAP 20 and 21, kind of sector-based controls. And you can see already here from the, if you have a system in California starting in January of this year, more than 50 pounds, you have to use a refrigerant with less than 150 GWP. Well, as luck would have it, CO2 is already there. It's an A1, it's available, it's being applied in California, those applications. You can also use propane currently in 150 gram charges. Or if your systems are less than 50 pounds, you can use SNAP-approved refrigerants per application, which are typically under 1,400 GWP. And there's some other limits on air conditioning. You can see there phasing in 23 all the way to 26. And retailers have some GWP targets that they'll need to meet. As you get into U.S. Climate Alliance states, there's 24 of them. Because the EPA did not have a national program, they decided to do their own. I mentioned California already, the purple state on the left, Washington above that. They've already implemented some of these rules. The yellow states, those have approved SNAP 20 and 21. The blue, light blue ones are in process of doing so. Again, these are sector-based controls with GWP limits of around less than 1,400. And then you got the green states that haven't really done any action yet. Move on to the federal, the EPA, the AIMS Act, December 2020 passed. Basically, it gives the EPA authority to do three main things: HFC phase down, sector-based rules, and HFC management. The highlight that I want to point out there is in 2024, which is what, 2.5 years from now, the baseline will be reduced, production baseline of refrigerant will be reduced by 40% based on the 2011 and 13 number. So that's going to actually put some stress on refrigerant pricing because of the availability. The cost will go up because the availability will go down. So CO2, again, looks very, it's a great choice of refrigerant that's available today to get ready for that date when it hits. And then as the industry starts to move to lower GWP options other than CO2 and naturals, then you've got A3s and A2Ls. And then you have to have product safety, UL, and application guidelines through ASHRAE. So that work is happening and near completion for A3 and A2Ls for refrigeration and air conditioning. And then you've got SNAP, the EPA division now that has to approve those refrigerants, lower GWP refrigerants, for those applications. And we're starting to see that. We saw chillers, now refrigeration, we expect that to happen in the near future. So that's what's going on there around HFC phase down. So why is CO2 a great option? Because number one, it's a natural refrigerant. Number two, it has zero ozone depletion. Number three, it has GWP of 1, and every other refrigerants are based off of that. And of course, if you use CO2 today, then you don't have to worry about any of these regulations going forward. So that's really what we're talking about, and we're going to try to build some confidence in application of some of those CO2 systems. So what you need to know before you start working on a CO2 system, some high-level things. We've broken it down, Brett and I broke it down into 5 main buckets. And we're going to cover those separately. High pressures, critical point, what does that mean? Why do we even need to talk about it? Triple point, standstill pressures and reliance on controls. So we're going to have a separate slide that covers each one of those bullets with comments as we move through the presentation. So those 5 bullets again, but before we get into specifically covering those, and because we're talking about CO2 transcritical system, booster system, and kind of directed to those who may be new to the architecture, I want to spend time to walk through the system a bit. Well, first we're going to start with the medium temp compressors. That really is taking in suction vapor and compressing it up to the discharge line. Now, those discharge lines are rated for upwards to 130 bars, so somewhere around 1,900 pounds. These compressors will have pressure reliefs beyond 1,900 pounds. So those discharge lines are either made of stainless steel or a ferrous alloy copper. So when you discharge into that discharge line, it's rated, it goes up onto the roof to a gas cooler rated for those pressures. And again, that line, gas cooler outlet line, hits a high pressure valve. That valve is nothing more than an electronic expansion valve rated for those high pressures. And it's there to drop that pressure from whatever it happens to be, 1,400 pounds or 900 pounds, but it drops it down to a usable form in the flash tank that'll be around 550 pounds. Everything orange here is at 550 pounds, that intermediate pressure. That liquid goes to your medium temp electronic valves, low temp electronic valves, and then your low temp will go to your compressors. You've got low temp compressors here that'll take on that vapor. You've got motor heat, you've got heat of compression. The total heat of compression gets discharged into the medium temp suction. That's one source of suction vapor. The other one is medium temp gas coming out of those coils, second source of medium temp compressor suction vapor. And the third source comes right here from the high pressure valve. As this, bypass valve, as the pressure builds up in the receiver, or what we can also call the flash tank, there needs to be a means of relieving that pressure to maintain a constant pressure within that tank. And that's the valve that does it. And it'll bleed it to suction, creating a third source of medium temp pressure for those compressors. So that's the general flow through a system. And we're going to talk about the various, those 5 differences with CO2 to HFC. So I'll start explaining the slide, then I'll pass it off to Brent. So high pressures, because first thing you hear when you talk about CO2 systems, oh my God, there's high pressures. Yes, they are higher pressures than an HFC system, got that. But where do they occur? It's important to understand that they only occur through the valve plate of that compressor, discharge valve plate, into that stainless steel line, which is rated for very high pressures, or ferrous alloy copper line rated for that pressure, going into a rated gas cooler back to the high pressure valve over here. So from that line up onto the roof back, everything downstream of that high pressure valve now is at a much lower pressure. You can see here will typically be below 580 pounds. So your discharge is pressure zone 1, flash tank zone 2, your medium temp will be your 3rd pressure zone, and your low temp will be your 4th. So Brent, when you're talking to young techs that show up at a job and maybe you haven't had any CO2 training, what are their thoughts about the pressures they see?
I mean, there's certainly some kind of fear factor in some of these young technicians or even advanced old timers, right? Not that they're all old timers, but they've been in the industry a while. So a bit of the high pressure and reading that seems to scare a little bit of people. But when we're out on site doing some startup work or doing some training on CO2, we try to strip back that fear of pressure. Again, going back through that system slide and the slide before this one where we broke down the components, the basics of refrigeration still apply. So when the guys start to understand that little bit of scare, a little bit of fear starts to fade back as we keep working through. Obviously stressing the importance that the system under pressure is dangerous, of course, but that's any system under pressure. So an HFC system can also be dangerous under pressure.
Right, thank you, appreciate that. So we get to the second point, low critical point. I'm going to talk about really low critical point. The reason we're talking about it is because CO2's point is low. It's only 87.8 degrees, and you can see it here, actually identified. And an HFC system is somewhere around 162 degrees. So we never get to that point, so we never have to talk about it. So if it's cold outside, like this morning here where I live, we're at about 68 degrees. So we would have been operating subcritically. So, but in the afternoon, we're going to be pushed up here in the supercritical zone. And the importance is that there is a point in which the system controller, when it gets close to the critical point, will take action and shift set points. And that's what we're going to talk about a little bit right now. The chart on the right, the bottom indicates gas cooler outlet temperature. The red indicates gas cooler pressure. And in the middle here, we talk about pressure set point. So Brent, can you explain to the audience here what happens when the system transitions from a subcritical set point to a transcritical set point?
Yeah, so if we base it back first at the subcritical set point, so trying to maintain a subcooling set point from the gas cooler to the high pressure valve. So we're running that on at about a 3 to 5 degrees of subcooling, depending on some of our OEM partners specifying what their system likes to run at. So when we're running in that subcooling set point, and as we see those ambients start to increase towards that 87 degrees, we get a drop leg temperature from the gas cooler. So between the gas cooler and our high pressure valve is now tipped over that critical point. We will change to what we call just a straight pressure set point. So anybody that's used to a condenser application running on pressure control, we're now running that high pressure valve at a pressure set point, because we've now lost some of that relationship for producing liquid or fluid, and we run the pressure set point to start taking some of that high temperature out of the gas to allow the high pressure valve to work the change of state of refrigerant there. But as you see on the right side of that, the graph there, as we phase out of a 87 degree drop leg temperature, coming back down into the cooler ambience through the evening, we'll transition back from a pressure control back into our subcooling set point. So trying to maintain a subcooling coming out of that gas cooler. There are some time delays in transition as well, so that we don't bounce too quickly between a subcooling set point and a pressure set point.
Yeah, that's a good point, because someone may look at that and say, why did it take so long before it actually transitioned back? And that's exactly what you just described there, right? Mm-hmm. Appreciate that. Thank you. So the other thing too is high triple point, something again we don't talk about with an HFC system. And the reason we say high triple point, you may look at the temperature and say, well, that's not very high. We don't typically in commercial refrigeration reach minus 69 degrees. However, we can reach 60 PSI very easily in a refrigeration system, and CO2 at only 60.4 PSIG, that refrigerant will turn to dry ice. So that's really important to understand, especially when you're charging a system. So there are obviously two different bottles. We know that every refrigerant bottle, regardless of what refrigerant's in it. There's a liquid vapor interface within that cylinder, liquid at the bottom, vapor at the top. So there are some liquid tanks that have special tubes that'll dip tube that'll pull a liquid off the bottom, and then your vapor tanks that just pull it off. So it's important to understand that if you've got low pressure, a vacuum, and you're trying to break the vacuum, you're starting to charge. You're not going to do it with liquid because it would immediately fill this hose up with dry ice, and everything will block off and everything will stop. And dry ice, incidentally, when it does, you can see the picture at the bottom there where there was liquid in that dryer shell, and the bolts were thinking that they had gotten all the liquid out, which they had not. They had turned it to dry ice. You pull the bolts off and boom, you got dry ice in the shell. And that dry ice does not expand like ice in an ice cube. It just stays in that space it was in without causing any crushing damage, if you will. So any notes there, Brent, related to guys in the field maybe experiencing dry ice?
Yeah, certainly. I mean, we see it's a telltale sign of a leak, for one, on a running system. As the CO2 is leaving the system through a leak point, you will see a form of that ice around maybe a service valve or a weld joint or something like that. But what typically helps to get rid of dry ice, if we do experience dry ice, is getting vapor in behind that dry ice again to get that pressure back up above about 100 psi. Otherwise, yeah, we could say go for a coffee or go and get some lunch, because it's going to take some time for that dry ice to naturally build its pressure back up.
Right. So you're driving the pressure up behind it to accelerate its subliming, right? Yeah, that's certainly it. And yeah, if you see that charging hose go stiff, it's normally a sign of a little bit of dry ice happening in that charge line as well. So sure. Things to be aware of. Great, thank you. Oh, safety. Look at the temperature at the bottom of that chart, minus 109.3 degrees surface temperature. So obviously when you're working around CO2, you've got to take care and use the right PPE when handling CO2 and or dry ice for that matter. The fourth thing we want to, from a difference perspective, is standstill pressure. Again, on an HFC system, when the system is off, the standstill pressure, this pressures that happen from the unit being off, don't even exceed the operating pressures. But on a CO2 system, other than medium temp discharge, the rest of the pressure zones, your intermediate pressure, your medium temp suction, your low temp suction, when the system is off, there is a potential for the pressure in those sections to rise above their operating pressures. Now, the flash tank, for example, will typically have a pressure relief of about 650 psi, roughly. Depends on the design, but something like that. That's 45 bar. So 650 psi, that tank will be typically operating around plus 40, which is 553 pounds. So if a system cycles off, either because for service, scheduled maintenance, you'll only have a certain amount of time before pressures will start to rise because of heat, refrigerant absorbing that within a constant volume will start to increase its pressure. So that's one thing to be mindful of on CO2 system versus an HFC system. Now, some of these larger refrigeration systems will have a auxiliary condensing unit with a UPS system that if there is a power outage or scheduled maintenance, you'll turn on that small condensing unit, keep the flash tank cool to keep the pressures down to give you time to work. Now, other systems may only have a UPS powering the electronic controls, maybe powering up a small valve that's connected to the flash tank that will burp when the pressures reach approach pressure relief rating. It'll burp to the outside and slightly reduce the pressure, bring down its saturation temperature, and give you a little bit of time. So there's different strategies that can be used. As you can see on the right, Pressure reliefs are a big deal, of course, on CO2. Every one of those pressure sections need to be properly protected with pressure reliefs. They're manifold, they're brought outside to an area that there's no one could be in contact with a blowing pressure relief. For example, this happened to be in New Brunswick by the Atlantic Ocean, thanks to Alain Mongrain for the photo. But yeah, so you've got to make sure that you meet codes and standards for that specific area. And the manufacturers have all that figured out for you, for sure. Brent, just wondering if you've had some experience with standstill pressures in the field with all these startups.
Yeah, certainly. During startup periods of, we're trying to do those in the cooler ambience to allow us some time to get up and running on systems. Also, you mentioned a little bit of scheduled maintenance there. So trying to schedule your maintenance around, ideal conditions, give you a longer time to do an oil filter change or to do a liquid dryers or things like that, So again, and stressing the importance for sure on the reliefs being piped out to the outside. If you've got an inside machine room or it's a rack house, that those relief lines are definitely piped to the outside atmosphere, away from any inlet hoods or supply fans that go back into the building, things like that. I like to stress that I'm a very safety conscious guy, so I want to keep that front of mind.
No, that's great. No, appreciate that. Thank you. And the last thing, I'm going to pass it over to Brent to talk about reliance on controls. That is his forte. Take it away, Brent.
Yeah, so we have a slide here that shows a traditional HFC centralized system, so a rack system that for those guys that are familiar with rack systems, this is what we saw pre-CO2 in most supermarket applications anyway. Very heavily mechanical control at the evaporators, and with TXVs, EPRs. You might have an E2 control running the rack, so doing your compressors and cycling condenser fans. But very, very heavily on the mechanical side. So, when you're doing your startup, there was a lot of manual setting of superheat at the evaporators, setting those evaporator regulation valves. It's taken a lot of time, a lot of hand tools from my past experience, carrying a lot of refrigerant gauges and temperature probes to do superheats and set EPRs, very time consuming. But as we transition into these transcritical CO2 racks and CO2 systems in general, is very heavy on electronic controls. Now, there's a few reasons why. There's a lot of pros in my mind of why how we get here with controls, electronic controls. Is we're managing safety of the system, managing pressures throughout the system, and that it also allows us to manage superheat at the cases electronically. We have pressure transducers and temperatures in cases or walk-in coolers. VFD driven compressors or digital compressors. The high pressure valve and bypass valve is also run by an electronic controller. And then the advantage of so much electronics on the system is that now you have a lot of eyes on the system that we've never had before in refrigeration systems, right? So a lot of data, a lot of touch points that we can see any issues arising or service problems later down the road, and help us troubleshoot a lot quicker. Very, very heavily on our electronics on a CO2 system for the positive, in my mind.
Well, Brent, I remember I've talked to a couple of years ago, I was talking to a young technician that he was the kind of the go-to guy to do CO2 service work. This guy was out of Quebec, and I asked him, I said, so do you prefer working on HFC systems or CO2 system? And, he told me hands down CO2. He says, I can troubleshoot this system from anywhere with electronics. Mm-hmm. So it's a huge benefit to him as a service technician. So,
Yeah,
great.
a lot of the end users out there are allowing remote communications through like Emerson's Connect Plus, where we can get in and look at these systems from afar. Where I could tell that the dairy case is having an issue with the electronic controllers showing me all the temperatures and pressures in that case. Where that was rolling a truck, less than 5 or 10 years ago for a lot of these end users. So cost savings to those, on their maintenance side too.
And one of the things too that electronics is allowed with CO₂ transcritical systems is designers to be able to optimize and add different high ambient strategies so that these systems are no longer just for Arctic countries. And you can apply these systems. They have been applied everywhere in the world now. And electronics is that enabler that, allows us to be able to do that. So great points for sure. So kind of dovetails into a little bit. I want to talk a little bit about high ambient strategies and understanding them for different regions. And as I mentioned, the ability to now install a CO₂ transcritical booster system anywhere in the world means that system add-ons in order to provide higher efficiency in those warm climates is part of our life now. And so Emerson actually invested. We reached out to a company called Future Green Now. They've been specializing in CO₂ for several years, over close to 12 years now. And we set out to understand the ambient impacts for the Americas. So we've got cities in Canada, about 166 cities in the US, and several cities in Latin America. And what we did is we worked with the consulting engineer to say, okay, well, we're going to use ASHRAE climate zones as well as the IECC climate zones, bring them together. We came up with 13 climate zones. We established what cities we wanted to look at, compiled all the bin data, the dry bulb temperatures, wet bulb temperatures, hours of operation in transcritical mode at temperature and subcritical mode, and looked at all that. We layered in high ambient strategies and did energy analysis using the EES software on a 400,000 BTU system at plus 18 degrees and a 100,000 BTU low temp at minus 20. That was our system we used. And we identified all the technologies. The main technologies were dry gas cooler is our baseline, base transcritical versus adiabatic. Then we layered in parallel compression on dry, and then parallel compression with adiabatic. And then we layered in gas ejectors, high pressure gas ejectors for both. So we did a complete analysis, energy analysis of all those cities, and then compared them to one another. And there's some highlights that came out of that. And if you're interested, I'm not going to go through that today, but if you're interested in some of those results, we'd be happy to share them. Reach out to your Emerson representative to schedule a meeting. So I just wanted to point that out, because now that allows us to have better understanding of our customers' pain points and to have some higher level value discussions with them. So part of the presentation here we call it system baselining, and this is, and also startup procedures, but this is information is presented. It's not meant to be a complete step-by-step process. This is kind of a directional process that we thought would be interesting because we've got Brent here and he's involved in so many of these. So from a baselining perspective, I mean, I'm not going to, picture's worth 1,000 words here about turning off power and working on electrical. But, when the piping perspective, I talked about this already. Some stores will use stainless steel. Others will use ferrous alloy copper. On the high side, of course, when you get into the intermediate pressure zones, you're going to be going to a type K copper. And even that, when you're in CO₂ system, you might get confused. And Brent, I think, has got an example of 5/8 lines being used in liquid as well as suction. And that can be confusing when you're piping systems up to make sure of that. But one thing's for sure, when you compare HFC to CO₂, because of the densities of CO₂, your line sets are incredibly smaller. The suction lines are much smaller. than they are on HFC systems. You might have a 4 and an 8 on an HFC system and something like a 1 and an 8 on a CO2. Very different. From a pressure test perspective, yeah, you're going to have to pressure test at about 10% above pressure relief values. So when you do that, of course, you can have your pressure release in place. And then you're going to be pulling a vacuum. And, you know, service techs have all their tips and tricks on how to put them quick, which hoses to use, how deep to pull a vacuum, typically around 250 microns to hold for at least 24 hours. And then you got to break that vacuum. And so I'll call on Brent at this point to, you know, how do you go about breaking that vacuum? And if you've got any other comments on these 4 things here.
Yeah, certainly. If I touch back on that piping comment you made, Andre, was, you know, a lot smaller pipes running throughout an installation, liquid and suction, right? And we've seen in the past where the piping guys have gotten liquid and suction lines crossed, or it's come from a factory that were incorrectly labeled, things like that. So just definitely paying attention to what your in and your out is out of your cases or your walk-in evaporators. You know, I saw in my previous life in another part of this world where even a rack manufacturer had to cross up a liquid and a suction header. So it even happens on that because similar size headers on the rack as well. So
Sure.
Definitely being conscious of which one's liquid, which one's vapor. You know, we find them in startup pretty quickly though, is in that we'll be reading liquid pressure on the suction line in that case, for instance. So it is, I wouldn't say easily identifiable, but we can identify it through starting up circuits where it has occurred, and we've gone beyond our vacuum and pressure test, and CO2 is already in the system. Where you know, so we do find those in some cases, and then you know, stressing the vacuum test and pressure test, and vacuum evacuation of, you know, the importance of that is we don't want to try and start a CO2 system up and have to re-evacuate, re-pressure test. You know, well, let's get that right. We take our time. The installers will get that right from the get-go. So that way, when we get into our vapor charge, you know, breaking that vacuum with the vapor above 100 psi. You know, we touched back on the dry ice and a little bit ago, and just making sure we're avoiding that dry ice section throughout our startup here.
Appreciate that. Thank you. A couple of other high-level things, because I've heard sometimes, you know, you get compressors and racks sent to the job site, and you don't have all the oil in there. And I think you're going to talk about that, Brent. And I'll give you the opportunity to also talk about, you know, connecting your supervisory control and the importance of all those connections. We've already talked about pressure reliefs and also check valves and confirming pressure safety. So as part of that baselining procedure, what are some of the highlights that you'd like to hit on today, Brent?
Yes, certainly the oil. So most of our OEM partners do ship the racks. So, you know, we ship compressors on CO2 systems, usually dry. So the rack will show up with no oil in it. So having to charge the oil on site. Typically, you know, the OEMs are supplying the right amount of oil to charge. So charging into each compressor and then into our oil separator and oil receiver. You know, we do certain steps through the startup to make sure that oil is flowing into those compressors the correct way with oil level control and such on the compressors, and then making sure there's oil in that separator and receiver for when we do need oil once compressors start running. You know, and with the controls, you know, now, like I touched on just before, was that we have so many data points in the system now, is that while we're verifying that things are ready to get running in a startup, we have all the transducer data there, temperature sensors. We can bump compressors to contactors and things like that through the controller, so that when we're ready to hit the go button and get this thing to run, that we're confident that we've gone through this controller and things are good to go.
Great. Thank you. So I'm going to pass it off to Brent here. for the startup procedures, as I mentioned a little while ago, it's not meant to be a fully inclusive because the rack manufacturers, they each have their own process of doing it, but I thought it'd be a great occasion to have Brent kind of walk us through this.
Yeah, certainly. So like Andre said, we pulled together just some over-encompassing points to verify. I've worked with most of the big OEMs here in the U.S. They, like Andre said, really have good startup checklists and step-by-step guides to go through for their system to make sure that we do it correctly, and then that also keeps their warranty intact. So, but what we stress is that, you know, it's taking our time for one. You know, a CO₂ system startup, we really only have one good opportunity to get this right. If you look back at an HFC system, you know, if we try to just start it up and we have an issue, we turn it off, we go and fix our issue, or we try again, right? You know, it's a little less forgiving that way. The CO₂ system, once we got CO₂ going into the system and pressures start to build and ambients start to rise, which is now bringing our pressures up as well, we really do only have that one good opportunity to get this right from the start. So a lot of these steps here is just making sure that our high pressure valve, bypass valve, and the evaporator electronic valves are ready to go. You know, they're wired correctly. We typically, when I'm on a startup with our OEM guys and a lot of the contractors out there, is that we'll go through and run these valves. We'll run them open, we'll run them closed. Are they stroking the right way? You know, we can do that with nitrogen in the system. It doesn't have to be CO₂, but we can run that valve. The electronics allow us to do that. You know, after we've verified those valves are good and that they're going to operate, you know, we're ensuring that the supervisory controls are good and ready to do it in a startup sequence. So as we go through to turn things on, the control will sequence the stages the correct way. Checking compressors, you know, we do that in a normal system, no different here. You know, if I ask for a compressor to run, is it going to run? Yes or no. The crankcase heaters are on. We're getting that oil warm before we start getting refrigerant coming back into that system. And then again, another one that no different to any other system is verifying the gas cooler fans are rotating the right way. You know, it seems like it's a yeah, no, of course they're going to be like that, right? But we do find, you know, phase rotation in the site is wrong. So it's spinning motors the wrong way and things like that. So they're definitely verifying that those gas cooler fans are rotating the right way. And then as we're bringing vapor into the system, now we've verified everything in the previous slide there that we're going to start bringing vapor in to start charging the system. You know, again, bringing it up to about 100 PSI on average. You know, the numbers can be a little bit less, a little bit higher, depending on OEM, depending on contractor as well. But middle ground's around 100 PSI. But again, our electronics are our friends here again, because now on the evaporators and the rack, I've got transducers all over the system. So now I'm verifying, I've got to 100 PSI on this vapor bottle going into the system. I can verify that I've got 100 PSI throughout the whole system now. Then that checks off my transducer as reading correctly throughout the system, cases, rack. You know, we'll have the main liquid line closed that goes out to the evaporators at this point, getting ready to start the system. So again, we have the flash tank bypass valve here. We can run this rack without evaporator loads or loads down in the store in the space, right? So this system can operate without evaporators if everything on top is good above the flash tank. And then we'll bring the evaporator valves over to the closed position as well, which will help us stage on evaporators one by one as we start up through the sequence. But I'll go through that here in the next slide. But you know, we're confirming that the flash tank bypass valve is operational. So is it opening and closing correctly? You know, it should be good because we tested that before on our manual stroke of the valve. But now we've got CO2 in the system. Are we seeing that bypass valve is actually taking load or vapor off the top of the tank? So once we go from there, we got compressors will start to cycle through the controller. So medium temp compressors, you know, compressor 1, is the VFD operational? When we command the VFD to run up, it's running up. Is it running down when we want it to come down? Then we'll test our fixed speed compressors. Compressor 2 turns on when it's told to turn on, number 3, and so on, depending on how many compressors you have. So now we've verified that pressure can move around the system and compressors can turn on and off. We're going to slowly open up that liquid line, or the main liquid feed to the store, or the evaporators. So now we're putting liquid down to the evaporators. At this point, we're probably about, you know, some of these flash tanks, they have sight glasses staggered up the flash tank. Usually we get to about the middle of the flash tank. There'll be a second sight glass. That usually is enough refrigerant in the vessel to get us to start running evaporators. And then as we've opened that valve up and we're getting CO2 refrigerant to the electronic expansion valve at the case, or the evaporator and the walk-ins. You know, we're watching that level in the flash tank. So typically you're charging at the same time as we start bringing on evaporator load. And we're starting with medium temp load. Highly important to run only medium temp loads at this point, because we're still testing that the system is operating correctly. So, you know, we'll typically bring on an open case in a supermarket application, something with a good amount of load that'll keep us running. So not a walk-in because it's an enclosed or a reach-in case. It's typically something that's open that keeps us on a constant load. So bringing that case and or that circuit lineup up and running, and then we're monitoring that. You know, is the case starting to pull down in temp? Is superheat starting to control the valve correctly? As we go through that, you know, again, slow steps, one by one, breaking it down, because we don't want to get too far ahead of ourselves if we have any issues to then double track back. But will engage circuit by circuit at that point in the medium temp application, and then start to mix in some low temp evaporators. So start bringing in those guys, which now is going to kick on our low temp compressors, start to give us some more load onto the medium temp rack. So now we're getting a good amount of load coming back to our medium temp rack, and we're testing low temp application. You know, compressors are running, digital compressor if we got digital, VFD if it's VFD, and evaporators are controlling correctly as well. So then once we go through all those, we're verified, we're starting to run everything. You know, we're watching the system, watching the refrigerant level. You know, are we adding in more refrigerant as we need it? And then once we go to full load capacity, it's just verifying defrosts and things like that. So we started, you know, back to a normal kind of startup that we would do with HFC. The defrost occurring, valves are closing during defrost. If there's heaters turning on, things like that, fans turning off, turning on. So, you know, at this point, we're still at a point where, you know, nothing really out of the ordinary to most of us guys. So with the E3 controller too, so we have a new E3 controller that is starting to come through with some CO2 applications or native applications to help us go through a CO2 system and startup sequence, a full integrated solution. So bringing it back into a user interface display here as well. So again, increased visibility, you know, a little bit easy to navigate through CO2 applications. And then the E3 will also give us the ability to customize the screen or the home page in the controller. So you can watch multiple things in the system occurring at the same time, rather than in previous renditions of controls. You got things in one screen, another, and another screen, and you'd have to try to customize something. But the E3 encompasses a more holistic CO2 solution with a CO2 applications. So yeah, the E3 controller, for those on the line today that aren't aware of the E3, so it will be an E2 replacement or an E2 drop-in product. It's the dimensions of an E2 box behind it, so it does become a true drop-in replacement as far as wiring and mounting holes are concerned. It does have an integrated display on it with a lot more visibility. More user-friendly customization, like I mentioned. So, you know, watching a system, so we can have logs and readouts all on the same screen, trending ability as well, and it is fully backwards compatible with existing multiflex and I/O boards throughout the system. I think we're running up a little bit of time here, coming into a close here. So. You know, we have just a brief overview of how the visibility of the user interface is on the E3 here, the responsiveness, and it's customizable or it's mobile optimized. So depending if you could use an iPad or a tablet or a phone to see the same type of screen, and it moves or shrinks and expands depending on your screen size. So, you know, good for us young techs out there that, you know, I like technology. I touched on a bit of the dedicated CO2 applications that we do have in the E3 controller. So dedicated CO2 suction groups for those that are used to E2s. You know, there's oil management control and injection control for hot gas and liquid injection. All within the suction group, not spaced across applications. We got a load management straight from that as well from the application. So again, it's not outside of the suction group. It's all programmed within that, and then we're monitoring our oil management of the system through that application as well. So if you're used to the E2, very, you know, bulletproof controller, as we know, you know, it's again just pretty standard screens, very little customization available. You know, just you have to go application to application. But on the right side with the E3, the CO2, we do have the customization of layouts and adding in trending tiles and more readout values to customize to the user. Visibility of the iPro high pressure valve controller and case controllers. So again, like I said before, a lot more data points available to us in the supervisory controller here. So, you know, really aids our startup and also our troubleshooting for serviceability. And then I just want to touch on the leak detection. I know we're running out of some time here, but leak detection is critical in a CO2 system, especially in a confined space like a walk-in or a machine room. So if we, in the event of any refrigerant spill in those kinds of spaces, you know, it's definitely important that we have a leak detection capability in those spaces. And some jurisdictions around the country do actually enforce this. So again, we know we do have a leak detection here.
Great, thanks, Brent. I'm just going to finish off. This will be our last slide here. Just kind of introduce to the group on the line that Emerson's getting ready to release these 3 white papers specifically geared to CO2, baselining CO2 refrigeration that Brent and I talked a little bit about today already. Then there's one on transcritical booster system design, some of the basic things that you may not be familiar with yet. And then taking the climate study information and starting to talk about the implications of climate regional adaptations on supermarket refrigeration, on commercial refrigeration. So those 3 white papers are coming out very shortly. So I'll pass it over to Kate. I think there may be some questions that have come in throughout the session, so we may have time for a few questions before we end.
Yes. Thank you again, Andre and Brent, for presenting. We'll just jump right in here. First question for Brent. As the E3 controller starts replacing more E2s for new CO₂ transcritical booster applications, do you have any tips on how to leverage the E3 for CO₂ more effectively during startups?
Yeah, I think I touched on it just a little bit ago. Is definitely a lot more flexibility and user these selectable points. Right, I've lost the word here, but you can customize the application screens more to the user. So a lot more information at your fingertips rather than navigating through the E2 between applications. It would be a keystroke from application to application. We can customize those views for different user levels or different profiles. So like an administrative versus a store manager or a service technician as well. So a lot more flexibility around that for sure.
Great, thank you. And then last question for Andre. With regards to the CO₂ climate study Emerson commissioned, did you notice any surprises in the results? And how can anyone get more information about the study's specifics? I know you touched on this a little bit.
Yeah, great question. I did find some surprises. For me anyway, I assume that a specific strategy will take adiabatic gas cooling would always win out over parallel compression in every single climate. At least that was my thinking until we started breaking down the data. So it was interesting to see that in regions where you already have high humidity, the gas cooler is already taking advantage of the moist air, and when you layer on parallel compression, you get an extra boost in capacity. And in some cases, parallel compression with a dry gas cooler in a specific region outperformed, from an energy perspective, adiabatic in that same region. You go to a drier region, that's not the case. But that was something that surprised me as I went through the data.
Great, thank you both.
Sorry, Kate, I didn't answer the last half of your question. If you're interested in learning more about the climate study, please reach out to your Emerson representative, and then we can find a time to go through the study with you. Thank you.
Great. Thanks, Andre and Brent. So that's all the time we have for questions today. Thank you again for your participation. Like I mentioned before, any questions that we were unable to answer during our time today will be sent out directly to the asking individual in the coming days via email. As a reminder, a few days after this live event, you can access this presentation on demand or view previous E360 webinars at e360hub.emerson.com/webinars, and you'll also receive an email in the next few days with a link to the recorded event. If you want to subscribe to our monthly E360 newsletter and access all of our E360 content, visit e360hub.emerson.com. If you'd like to explore today's webinar topic further, please visit the links found within the resources tab shown on the screen. Please note a survey will appear after the webinar has concluded. We would appreciate your response and hearing your feedback. On behalf of Emerson, thank you for attending today's E360 webinar. Information and registration will be available soon for our next upcoming webinar. We hope you can join us again. Thank you.
Thanks, everybody.
Thank you.